Swayam Prabha. Digital India. Educated India.
So, welcome to lecture number 35. In this particular lecture, we will start this modeling and management of groundwater. And under this, we will cover groundwater simulation models and groundwater management models, and particularly for confined aquifer. So, under this modeling and management of groundwater, it has got two aspects. One is simulation aspect, another one is management aspect. In simulation aspect, we try to see the physical processes by using our governing equations that we have derived in our previous lectures, and in management model we try to see what if kind of scenarios if we do certain kind of management, or we put certain kind of restriction on the groundwater use, or restriction on variables, then what will be the situation in near future or in long term aspect. Okay. So, in flow equations under modeling, that has got two components. One is the temporal component and other two parts are spatial based components. So, in this one, the first one, this epsilon, this is basically porosity, then we have water saturation and fluid density. So, basically if this combined term, the multiplication of porosity, water saturation, fluid density, this is temporally varying, then we can say that either we can model that density dependent or density independent phenomenon. For density independent phenomenon, the equation will be slightly modified because it will not be varying with the density aspect. So, other parameters in this equation, solid matrix permeability tensor, we have fluid viscosity, this is basically dynamic viscosity of the fluid, then relative permeability and fluid pressure, we have fluid mass source So, in the flow equation, this rho value or this g value, this is having only component in the vertical direction. So, this is basically a modified form of our Darcy's equation, if we consider it with the fluid pressure term. Next word is saturated unsaturated transport model. So, this is basically porosity, water saturation, density, and this is dissolved mass fraction. Then volumetric adsorbate source, other things, that is average fluid velocity. Then we have apparent molecular diffusivity and identity tensor, and this is dispersion tensor, and this is our mass solute mass in source fluid due to production reaction, and this is QP into C star. This is C star is basically solute concentration of fluid sources. So, our solution methodology is basically solving the basic governing equations. So, what are the basic governing equation we have covered in this particular course? First one is Darcy's law. This is our most fundamental equation, that is relates the equation of motion, or if we say that is one form of our Navier-Stokes equation if we compare it with fluid mechanics. Then we have equation of continuity, that is mass balance equation, and finally we have solute transport equation or advection dispersion equation. In advection dispersion equation also we can have other components like adsorption, including isotherms, or our radioactive decay, and these terms will be there to model the whole thing. Now, these three equations are our fundamental equations. These are basically if you consider it in one dimensional, then it will be mostly if you are considering a steady state case, then it will be normal differential equations or ordinary differential equations, but most of the cases it depends on both space and time. So, these equations are basically partial differential equations. Then we need boundary conditions. So, boundary conditions and initial conditions. So, for a particular problem we can have either a initial value problem IVP, partial differential equation, IVP or initial value problem, or BVP or boundary value problem, or IBVP or initial boundary value problem. So, our equations are mostly in these two forms, So, solution can be obtained for these two equations using either analytical or numerical methods. So, to solve these two or solve this equation in form of analytical solution, we need to have some kind of simplified form of the equation. Otherwise, it is difficult to find out the complex the analytical solution for a complex hydrogeological system. Numerical solutions are easier to find out because we generally used a discretized form of the equation, and we try to solve it with algebraic equations. So, in case of numerical methods, either we can use this finite difference, finite element, finite volume, SPH, that is smooth particle hydrodynamics, spectral methods, or any mesh free methods for this purpose. So, what is the conceptual form of calibration? So, first we need to have some kind of definition, or we should have proper definition of our purpose. What is our objective? Whether we want to model the thing or we want to model it for some kind of management strategy. So, we will have some kind of field data, and from field data we can create the conceptual model, that is conceptualization of the mathematical model. So, we need to identify the governing equations that will be required for a particular problem. So, identification of governing equation, then boundary condition, initial condition. So, next thing is numerical formulation. Numerical formulation, we can discretize the equation, we can write the computer program. Code verification, this part is important because we need to have some kind of verification of the code with the existing solutions. So, solutions can be either existing analytical solutions, so or existing solution for a 2-dimensional problem, but 2-dimensional problem or 3-dimensional problem, the problem is that if we start with the reality thing, then there will be certain kind of errors. So, it is better to use that analytical solution for code verification. So, if the code is not verified, then we can go back to the computer program and we can try to rectify or correct our errors. So, code selection is important. So, either one can write his or her own code, or one can select a proper code which is either a open source or a commercial one. So, if code verification is complete or code identification or code selection is complete, then we can go to this model design part. So, with the field data we can design the model, then calibration, comparison with the field data. So, one way model verification is done and calibration is done, and this calibration should be supported by the sensitivity analysis. With the sensitivity parameters, with the sensitivity of the parameters, there should not be much change in the model results, because if we are identifying the parameters in such a way that it is not a proper identification for which there will be not much variation, then it will be a problem. So, we should have proper identification and sensitivity analysis with our problem, and then after model verification we can go for simulation. With simulation also we can correct our sensitivity analysis, and final is presentation of the results. If there is some kind of monitoring network, then finally we can monitor the thing and we can correct our assumptions or conceptualization with those monitoring data, and again we can start from the initial part and we can conceptualize the thing and we can redo the whole process, so that we can correctly adjust the model to get the proper results. So, code selection in this case is an important part of the modeling exercise. Either one can have one can have their own code, or they can readily select some codes which are available in public domain. So, standard simulation models that are available in the public domain or with some restriction or in commercial domain, this is one comprehensive list of those models. So, first model is the mod flow. This is basically 3-dimensional finite difference based simulation flow simulation model. This is FEM water. This is 3D finite element model for saturated unsaturated flow through porous medium. See what this is saturated groundwater modeling or density dependent groundwater modeling in coastal aquifers. Sutra, this is saturated unsaturated flow and transport model. With this we can model it the groundwater flow and transport in any kind of aquifers. MT3DMS, this is for contaminant transport with multiple contaminants. RT3D, this is reaction with reaction. MOTPLOT is flow path identification thing in groundwater. Then SHARP, this is a 2-dimensional quasi 3D simulation model for saltwater intrusion modeling, and this is based on SHARP interface. Then HS3 3D, this is this includes also that heat transport part. Other models that can be named here are this hydrotherm, FAST, this also include the chemical reaction part, tough to flow through fractures media, Flowtron, ITUF, the inverse tough thing, Bioplume, this is one. Hydrus, this is also important software to model the flow in unsaturated porous medium. So, so the identification or selection wise we can select any of these models for our modeling purpose, or we can discretize our governing equations and we can use our standard discretization methods to get the solution. So, this is the starting of our modeling exercise. So, in modeling and management of groundwater, we have two aspects. One is the modeling aspect. In modeling aspect, we will see what is the simulation results, and the policy aspect or management aspect, we try to formulate some kind of management strategy. So, for hydraulic management, I am talking about the hydraulic management because if we are talking about the flow part only, then only we say it as hydraulic management. Otherwise, we need to have certain kind of management models with transport mechanism. So, in case of hydraulic management, hydraulic management, we can have equations in the form of embedding technique, embedding approach. In embedding approach, the governing equations are directly discretized and these are used within the optimization model or decision models to get the solution. Next is our linked simulation optimization. Simulation optimization. In linked simulation optimization, the simulation model is directly linked with the optimization model or decision model to get the solution. So, first approach, in embedding approach, we generally write the equation in discretized form and we directly use it in the decision models to get the results. But the problem with the embedding approach is that as we are discretizing it for a number of points or for a number of grids. So, number of decision variables, number of variables, that is crucial for this kind of approach. But in case of linked simulation optimization, the simulation model is doing the simulation part separately and only with a limited number of variables we can solve the decision model. So, first approach concern is variable, number of variables. The second approach, the concern is simulation time. If we are setting up a complex simulation model, then for each simulation it will take significant amount of time and that will be a limitation for this linked simulation optimization. Then the third approach which can overcome these two limitations, that is called meta model approach. Meta model approach. In this meta model approach, basically meta models are trained with the simulation results from original simulation model, and we try to minimize the meta model error between the meta model output and the output from original simulation model. So, at each iteration there will be correction in terms of correction of errors, and that can be assessed with certain kind of indicator reference functions. So, in meta model approach, the most primitive approach is response matrix. Most primitive approach is this response matrix. So, response matrix approach, what is the advantage? Advantage is these are basically linear type. With the linear type of response matrix thing, we can easily form some kind of linear model based decision model, and we can quickly get the solution. But the problem is that response matrix will always give you some kind of linearized results, and one way we are compromising with the accuracy of the simulation model. So, for a complex nonlinear general equations or general problem, we cannot represent it properly with our response matrix approach. So, we need to have certain kind of approach in which we can consider that linear model thing, nonlinear model thing. So, nowadays people are using this ANN, SVM, GP based models. So, what are these? ANN is artificial neural network, SVM is support vector machine, and GP is genetic programming. These models can consider or can represent the nonlinear behavior of the complex hydrogeological system. So, now we can have the approach where we should be defining our equations, then some optimization methodology, and then we should have the solution. So, first part is simulation model, that is original simulation model or a meta model, then identification of objectives, constraints. So, from simulation model to identification of objectives, constraints, then based on constraints and objectives, whether they are linear or non-linear, we can find out the optimization approach slash algorithm. So, this is the process where first identification of simulation model, then identification of objectives, constraints, then depending on linear or non-linear behavior of the objectives or constraints, we can identify the optimization algorithm. So, let us start with the simulation model. So, for as per Darcy's law, we know that Darcian flux V for any confined aquifer, that is for any confined aquifer can be defined as V del H by del L. So, this is basically head loss per unit length, head loss per unit length. So, now with this we can have one finite difference grid So, these are basically nodes. So, black dots are nodes. This is level say j plus 1, this is j, this is j minus 1, this is ith cell. So, del x I, and let us say that q 3 is entering, then q 2 is leaving, q 4 is leaving, and q 1 is entering, and this is your del y j. So, basically this is cell to cell water transfer. So, here we can say that this q 1 is basically minus T x I minus j del y j by del x, this is 1, this is q 2 is basically T x I j del y j del x, second one, this is q 3 is minus y I j plus 1 del x I del h by del y, third one, and the fourth one and the final one is T y I j, that is del x I del h by del y 4. So, in this case T x j is the transmissivity in the x direction of the element I j. So, and T T I T I j, and this is 2 element I plus 1 j. So, from this point to this point, so in this direction this T x I j, that is acting. So, rate at which water stored, that is rate at which water is stored, that is considered as Q 5. So, S I j, where S I j is your storage coefficient, this is del y j and this is del h by del t, and in addition to that flow rate Q 6 for constant net withdrawal or recharge So, Q 6 is basically Q I j and T, this is varying with T. So, by continuity continuity equation may be with the continuity of the flow, we can write it as Q that is entering, Q 2 that is leaving, plus Q 3 that is entering, minus Q 4 that is leaving the thing, and Q 5 is again that is the rate at which it is stored. So, it is equivalent to the storage plus Q 6. So, with this if we replace all these previous expressions for Q 1, Q 2, Q 3 and Q 4, we will get this is T x, this is del h by del x 1, this is del h by del x 2, this is del x I and this is T y. With this del h by del y, del h by del y 4 and this is del y j. So, S I j del h by del t plus Q I j t divided by del x I and del y j. So, for infinitesimal values of del x and del y, we can write the equation as T x del 2 h by del x 2 plus T y del 2 h by del y 2 s del h by del T w. So, if we talk about finite difference thing, then we can write this equation as del h by del 1, and this is basically j t and h I j t del x I del h by del x for second phase, that is I j t minus I plus 1 j t divided by del x I. So, del h by del y third one or third phase, that is I j plus 1 t minus I j t divided by del y j, and the last one, that is the fourth one, is I j t minus h I j minus 1 t del j. So, with this and del h by del t is h I j t minus h I j t minus 1 divided by del t. So, if we substitute these 5 expressions in our previous equation, then we will get a compact form of the equation in terms of a I j h I j t plus b I j h minus 1 j t plus c I j and h I plus 1 j t plus d I j I j plus 1 t plus e I j h I j minus 1 t plus f I j t equals to 0, where these terms are basically coefficients involving our known values or provided information. So, this can be solved using any standard numerical technique like ADI or alternating direction implicit method, alternating direction implicit method, or this is the form of the discretized equation. These can be directly used for embedding purpose. Now, we are concerned about the management model and groundwater management model. There we are concerned about the confined aquifer. So, in case of confined aquifer, let us say that our configuration is like this. This is the base or lower portion, then we have in between the impermeable part Q1, this is Q3 and this is Q4. So, basically this is the aquifer material there, and this is the water height which is H5 at this level, and all are having equal del x difference, and on the left hand side we have H naught value of the water level. So, it is a bounded problem. Both cases we have specified boundary condition. This is also called as Dirichlet kind of boundary condition. So, for this kind of equation we have del H by del T del H by del x equals to W by T x, where for a steady state condition we have T equals to del H by del T equals to 0. So, for this kind of equation, let us discretize it using our normal finite difference method. For two second order finite difference, we will get del x square W I T x. So, this is the discretized form of governing equation, and we have 1, 2, 3, 4 pumping from this particular aquifer, and this H naught and H 5 are two water levels on left and right hand side. So, our objective is to maximize. So, first we have completed the simulation part. Now, we are concerned about identification of our objective function. So, objective function is maximization of our total head for I I that belongs to the set of I, that is the set of wells and this is subject to or ST we can write it as this I, this W I is greater than W min, and H I is greater than equals to 0, Wi is greater than equals to 0, again I belongs to that set I. The W min is the minimum total production rate. So, rate for the well. So, the total rate should be greater than or equal to the minimum rate that is specified. So, unknown for this problem are unknowns H and W. So, once the model is solved, this can be determined, W can be determined as Qi divided by Xi del Xs square. So, head objective that thing is for managing the aquifer. So, the above formulation, one limitation is there, that is it considers negligible well diameter and negligible well losses. So, for any example problem, we can define the same thing, using our this particular approach. So, for our original problem, we can write the equation as the maximize Z equals to H1 plus H2, H3 and H4, and this is subject to our finite difference equations, and that is minus 2 H1 plus H2 minus del x square by T W1 minus H naught. This is H1 minus 2 H2 plus H3 minus Wx square by T W2 equals to 0, 2 H3 H4 minus del x square Q3 0, this is H3 minus 2 H4 del x square T W4, this is minus H5. So, we have defined our constraints, and the final constraint is this one, that is there is a minimum value of total pumping in production wells and Hi greater than 0, that is I equals to 1 to 4, and Wi that is also positive I 4. So, in this model uh, additional constraints, we can put that H4 should be greater than H5, then H3, H4 greater than 0, that means H2, H3 greater than 0, and H1 minus H2, that is greater than 0, and finally H1 is greater than or less than H naught. That means your head on the upstream direction, or you can say that where we have a higher head value, that cannot exceed or that cannot be a lower one compared to your down gradient value. So, these are the additional constraints that will be required for solving the thing, and the full equation, as because this is linear in nature, we can solve it using LPP. So, this is all about the management of confined aquifers. Okay, thank you.